you, David.
So this is work that was done in collaboration with AT&T Labs. It's a very practical piece of work. So it's the principal author is here, Siddharth Satpathy, and also Supratim Deb and He Yan from AT&T Labs. Okay. So the problem is one where we are given lots of error messages from a network, and you have to figure out what error events contributed to these error messages. Okay, and I'll explain further. So this is probably applicable to any kind of distributed data center setting, but I'm going to primarily focus on a data center network that supports wireless networks. Everybody knows what a data center is. A data center is a large collection of servers. It's used by all the major companies that you can think of these days. And the data center network is a network of these data centers. So each one of these is the picture that I showed in the previous page, and they're all interconnected. They're geographically distributed, and they're interconnected in some fashion. So normally when you think of distributed data center networks, you think of Amazon, Google, Facebook, and so on. But it's also used by banks, and it's also used by AT&T, with whom we collaborated on this project, and Verizon, Sprint, and all major wireless service providers. So how does AT&T use distributed data center networks? So normally when you think of wireless network, you think of a cell phone, which is trying to access some base stations and so on. But supporting this wireless network, there is actually a distributed data center network in the background. Okay? And it does a lot of things, and I'm going to give very, very simple examples of what it does, but it does a lot more than what I'm going to explain here. So as an example, let's say my postdoc, Wayna, who's been visiting Simons Institute with me, she's normally in Illinois, and she's making a phone call from California. So there is a piece of software that's sitting in some data center here. You can call it a virtual machine. And it sends a message to a database in Illinois to authenticate whether this is really Wayna. Has she paid her bill? Has she exceeded her voice call limit? Has she exceeded her data limit? All of these are done actually before you complete the phone call. Okay? And this message from this data center might have to be routed through some internet router to some other data center here. Then from there, it goes to the data center in Illinois. Okay? So what happens if there's a failure, if there's a router failure here? Okay? So then the network generates many messages at various locations in the network. So there's one message that says that the router's fan is broken down. Okay? And this data center would realize, the data center in Illinois would realize that its connection to the Colorado data center is no longer functioning. And the California data center would generate a message saying that I'm not able to validate if this is Wayna, for example. Okay? So these are the messages that are generated due to this router failure. And similarly, somebody else, another one of my students, Harsh, is calling Joseph, who happens to be here. And let's say there is a loose connection in a line card, which may not even generate an error message by itself. But the Harsh's call to Joseph cannot complete because of some unknown error in the network. So that also gets entered into this central error log. Okay? Of course, here I've color-coded it to let you know that these red messages are due to one event, and the blue messages are due to another event. What you actually see is just a sequence of messages. Okay? What you see is just simply a sequence of messages. From this sequence of messages, you have to figure out how many events happened in the network, when these events happened, and what is the distribution of messages that each event generates, the probability distribution of messages that each event generates. Yes?
Are we assuming the clocks are synchronized?
Excuse me?
Are we assuming the clocks are synchronized? So
the clock is not that important. I mean, so the messages are sufficiently far apart that this is not an issue for me. Yeah, good question. Yeah. So the size of the data set that I'm dealing with, what was given to us by AT&T was a 97 million message set collected over a 15-day period from their network. And as I mentioned, this is not, most of the messages are actually generated by VMs in data centers. So there's something called virtualization. If you're not familiar with it, it doesn't matter. Basically, there are more and more software entities being added to the network. Each piece of software is bought from a different vendor. Each one generates its own error message. It's not coordinated. There's no standardization of any of these. And so you get this massive, humongous set of messages that are being generated in the network. And a failure in St. Louis could cause messages from all over the United States, for example. Okay? And the goal is to take this 97 million message data set and break it up into events. Okay? Events meaning there is one event that started at 1 second, ended at like 1,000th second or whatever. And then you also have to figure out what is the distribution of messages it generates. So we'll make it a little bit more abstract, then it'll be actually clearer what the problem is. OK, so what's the modeling? So the modeling aspect of this is, so I'm going to assume that each event generates messages. And I'm going to just color code the messages. I'm going to call them red messages or green messages or blue messages and so on. So what I showed earlier was like a detailed descriptive message. But what we do is we do some natural language processing on it and then reduce it to a smaller subset of messages for reasons that I don't want to get into. So for the purpose of this talk, let's just say that each event consists of a bunch of messages, red, green, blue, black, and so on. And each event has a different distribution over these messages. For example, some events might generate 50% of the messages it generates might be red messages, whereas and 25% might be green and 25% might be blue. Whereas another event might generate 25% red messages, 50% green messages, and 25% blue messages. Okay? So this is what I mean by an event. And an event also has a start time and a finish time, during which time it keeps generating messages according to some point process, some unknown point process. So essentially, the way we can think of this problem is that there's event 1 that happened. It started here, started at the leftmost point, and ended here. And then this event 2 started in the middle of event 1. It is generating its own set of messages. And what we see in the central error log is both of these sets of messages merged together. Yes?
Do you know which events you're looking for and what these distributions?
No, we don't know anything. So we don't know anything. All we are given is just a bunch of messages, and it's an unsupervised learning problem. There is no expert in AT&T that knows which events generate which type of messages. Nothing is all we were given is just a 97 million message data set. That's it. Nothing is known. Yeah.
How many colors do we have?
So in this problem, it's about 1,000 colors actually, and 97 million messages. So it's still it's at least more than square, 100 times the square of the number of messages. So we are operating. I don't know what the question meant, but if you're asking the question, are we in an information-rich regime? We are. I mean, the number of messages is an order of magnitude smaller than the number of events. If they are roughly equal, then that's a completely different problem. Yeah.
Number of messages smaller than?
Number of messages, the different types of messages is much smaller than the total number of messages. There are like 1,000 different types of messages, and the total number of messages is 97 million. Yes?
Similar question. How many different types of events do you expect to have?
So during this time, there were about 20 or 25, actually, or 15 major events, yeah. The network is pretty good. I mean, it doesn't fail that often. Yeah. Yeah.
Event is the fan is broken, or the event is that
the fan is broken is an example of an event, but that's not what machine learning is going to tell us. And that's usually it's not that type of event. As I mentioned, because of virtualization, all you're going to know is that this piece of software was not able to talk with another piece of software, and could be all kinds of errors. It could be a hardware error, it could be a software error. Mostly the software errors. Okay, so all they're interested in is figuring out what distribution of, by an event, what I mean is a distribution over messages. That's it. So the final answer they want is, I have 15 types of events. Events of type 1 produce, this type of messages or this distribution of messages. And then the idea is that they are, I don't know if I'm allowed to say this, but when I'm being recorded, but I'm going to say it. They are interested in operationalizing this. Maybe edit this part out. And they are interested in operationalizing this. So the idea is that as you see a certain mixture of messages, then you can sort of predictably, I've seen this problem before, and so maybe perhaps you can take a corrective action. Yeah.
Sorry to drill on this. So just following up on Eva's question.
Right.
So you said 20 to 25 events or types of events? 20 or 25 types of events?
Yeah. Well, actually, there are only 25 events.
For 97 million messages.
97 million messages. Yeah. That's pretty information-rich regime. Yeah.
25 events and 1,000 messages.
Message types.
Right. So the point is that a single event just, creates messages all over the network. That is the big difficulty here. The enormity of the message log is the problem, and there is just, yeah, exactly. There's just a massive number of messages that each event causes, because it's a massive, massive network. I mean, I don't even know how many routers and how many base stations and how many optical fibers are involved in this. Yeah.
Following up on sort of understanding.
Yeah, good. Yeah.
But with the start and end times, that's 20. I mean, how many concurrent events are likely to be?
So we have at least 3 or 4 sometimes. Yeah. But of course, there are lots of times where there is no messages. Yeah, I mean, nothing happens in the network. I mean, it's collected over. Yeah. That's how it should be, right? Yeah.
The event has a unique signature?
Yes, that is our assumption, and it does. Yeah. We validate it in various different manners. Because this is an unsupervised learning problem, it's kind of hard to validate. Depending on the time, I'll talk about how we validated it. Yeah.
Another stupid question.
No, not all of these are good questions. What's that?
You're making the assumption that this one event will generate a fixed distribution
Right.
over time. Like, if half of the messages are read or
Yeah, exactly.
half are read, and that's true in the beginning and the end.
That's right. And roughly speaking, this is borne out in the message set. And the reason is, I think during the occurrence of an event, so many different types of functionalities are carried out, and the same set of functionalities happen in the network over and over and over. Every time somebody initiates a call, or maybe there's a power control algorithm running in the data center, which actually computes, the power control parameters for the 4G network, for example. And so exactly the same set of functionalities are executed over and over, and every time it tries to execute it, it's going to generate a message, and so we see the same thing over and over. Yeah, good question.
So
Yes?
are you trying to solve the sequential problem that all this message comes?
It's not a sequential problem. This is given to us. This is an offline problem. So the sequential problems, once we've done this, what they are trying to do is use this information to figure out, as messages are being generated in the network, to see if this is something we have seen before and what did we do at that time. Yeah. Anything else? Okay, so I'm going to make a complete digression. I'm going to talk about topic modeling in documents, and I'll relate this to our problem. So that is basically the primary contribution of this work, is basically somehow convert our problem to a topic modeling in documents, which is a well-studied problem. Okay? So in the topic modeling problem, you're given multiple documents, and you have to figure out what topics generated these documents. So obviously, this is probably politics. This document probably is about sports. And this is probably a mixture of politics and sports. Okay, so this is a very famous algorithm that many people, I guess, Andrew Ng and Michael Jordan and David Blay studied. And so in topic modeling, basically you give these documents as input, and the output is basically there are 2 topics here. Of course, machine learning will not be able to say this is sports or this is politics. Maybe it will, but basically the output is basically there are 2 topics here. Document 1 is generated by topic 1. Document 2 is generated by topic 2. And document 3 is a mixture of topic 1 and topic 2. And what a topic is just a probability distribution over words. Okay? This is a well-studied problem. If you give documents to this algorithm called LDA, so LDA is a well-studied algorithm. So LDA is an algorithm which basically you give it documents, it'll output the following, which will say each document is a probabilistic mixture of certain topics, and each topic is a probabilistic mixture of words. Okay? So I am going to assume LDA as a black box. So my only goal here is to convert my problem to document modeling, and after that I'm just going to use off-the-shelf software to solve the problem. Is clear? So I have to figure out, so in my model, topics are the same as events. So what I call events are essentially topics in document modeling. What I call messages are words in document modeling, but I don't have a notion of documents. So what we are going to do is come up with an efficient algorithm, a linear time algorithm, to convert my problem into this problem. In other words, I'm going to take my message set and break it up into documents in linear time. That is basically the contribution here. Okay? Is this clear? Okay.
So just to be, the messages are somewhat literally like the way you showed it, like the red.
But we process it. We do some natural language processing to extract what are called templates out of it, the key important parts of it, and that is slightly difficult. I mean, you don't ever work with actual raw data when you do this kind of a so you extract the key features of the messages, and there is an entire NLP thing, but we just crudely used.
You can take it for this talk that it is looking like the red
Exactly.
and blue stuff that you have.
Exactly. So that's the model is very important. So basically, I'm going to assume that there are X types of messages, and each event is a probability distribution over these messages. That's it. Okay. Good. So basically, the idea is, what are documents? Documents are what so I'm going to define something called an episode, which is the equivalent of documents. So if you look at this set of events, there is a transition point here. There's a particular distribution of messages that happens here because there's only one event. At this point, this distribution changes because there are two events happening. The first event ends here, and so the distribution of messages changes again. So each of these intervals I'm going to call episodes, and these episodes are going to be like documents in document modeling. Okay? So the whole problem then boils down to finding episodes, and if you want to precisely define what an episode is, within each episode, the message distributions are IID within an episode. The interarrival times of messages I'm going to assume are IID. And I'm going to assume successive episodes contain different message distributions. And between successive episodes, I'm going to assume that only one new event starts or one current event ends. Okay? So this describes an episode.
Are you saying all messages are IIDs, all messages types? The type of a message in an episode is IID?
Yeah, that's right. Each message is generated according to some probability distribution, which is IID, within this episode. And then this distribution changes here. So here it might be 0.5 red, 0.25 green, and 0.25 something else, whereas here it might be different, yeah. Okay, so the goal is to break up the very large error log, 97 million in our experiments, into episodes, and then once I've done that, I'm just going to use LDA. So the whole problem is just finding these episodes. Yes?
So if you always had a green message trigger a green message, a green message.
Yeah. So that
would work.
Yes. So this appears to work. So we have been thinking whether one could use Markov modeling or something like that, but this works remarkably well. So we haven't done anything. But these are all interesting problems that we can sort of make up to work on further. But I think for the problem that we were given, this works very well. Yeah, good question. So what is the algorithm? So basically, the algorithm is change point detection. I mean, should have been obvious. Essentially, these are points where the distribution changes. Okay, so there are two distributions involved here. One is the interarrival distribution of messages. If there are multiple events occurring, messages will be generated faster, and also the distribution over the messages themselves are changing. But it's a non-parametric change point detection. I mean, classical change point detection, you have some hypothesis 0, hypothesis 1. I mean, you say that at some point there is messages are generated according to some distribution beyond some point. You're given these things. Here, nothing is given. Okay, so this is a non-parametric change point detection problem. And we want to find an efficient manner. So the whole key is that there are 97 million messages. So you have to process all the messages at least once. So it has to be linear time at least. Okay, but it can't be square of that. I mean, it has to be small. The complexity has to be small. That is the basic problem here. So the basic idea is that, of course, you would guess that there is a change point at a particular location, and then you estimate the distribution of messages to the left, estimate the distribution of messages to the right, and then you declare the change point as the point where this difference is the largest. You sweep through this whole message set and declare that is the point. I mean, of course, you might have a threshold. You might say that if this difference is above a threshold and if it is maximized at some point, you declare that's a change point. But of course, that doesn't work when there are n messages and k change points, right? If there are n messages and k change points, there are n choose k possible places where the change point could occur. And this is ridiculous complexity. You can't search over this space. So the question is there a more efficient algorithm? And we used this idea that was proposed by Mattison and James, who used a different metric. And I'll tell you what we can't really use their metric for our problem. But we use their high-level idea. So what you do is you find the change points in hierarchical fashion. So the idea is this. So what you do is you first pretend that there's only one change point. This is not correct. Right? You pretend that there's only one change point, find the change point, and then divide the problem into two parts. So you look to the left of the change point that you found and find more change points, and look to the right of the change point that you found and look for more change points. Okay? So this is the idea. Is this clear? Is the algorithm clear? OK. And in this problem, if you apply this, then you'll detect 2 change points. And then after that, we apply LDA. So we have our documents. We have our words. And we have to extract topics from this. And then we just apply LDA to this problem. OK? And LDA will say there was 1 topic here, 2 topics here, and 1 topic here. Okay? And from this, you can easily disentangle and say that there's a topic 1 started here and ended here, and topic 2 started here and ended here, or event 1 started here and ended here, and so on. That's very easy to do after this. Okay? So from an analysis perspective, the main thing we need to do is, showing that this has a computational complexity that is order n times m times k is pretty straightforward. That's pretty straightforward. The hard part is this, that is consistency. So what you need to prove is that when you do this hierarchical change point detection, you have to show that every time you actually find a true change point. Okay, the first time you're pretending there's only 1 change point when there are k change points. When there are 20 change points or 25 change points, you pretend that there's only 1. Okay? And you have to show that when you do this, you actually find a change point. And when you hierarchically do this, you actually find all the change points. And what we do is, what we show is that the normalized change point, if there are n messages, and tau1 hat is the location of the first change point. In a relative sense, tau1 hat divided by n is the location of the first change point. What you show is that we show a consistency result. In the limit as n goes to infinity, all the change points are detected exactly. So there are no spurious change points when you execute this algorithm. Okay, that's the first result. The proof of this, maybe I'll skip it. Essentially, the idea is that, it's a somewhat involved proof. This is the main difficult part of the proof. It's a somewhat involved proof showing that you have consistency. Okay, so you don't get spurious change points. The second result is a sample complexity result, which tells you how many samples do you need to get all the change points to detect all the change points with probability greater than some 1 minus beta. And that again, now it's, this is actually relatively straightforward because essentially you're estimating probability distribution. So the natural thing to do is use Sanoff's theorem and then approximate the KL distance by Pinsker's inequality, and then you get this result. Okay, this is a relatively easy part. I think the consistency part, is the harder part of the result. Okay? So I'm going to talk about experiments before I wrap it up. So validating this is very, very difficult because there is, as I said, it's an unsupervised learning problem. So there's no easy way to validate it. So what we do is we take the data set and apply other algorithms which give partial answers, okay, and see if our algorithm actually matches those answers in those cases. So one simple algorithm that people use often is a clustering type algorithm. So basically, each of the messages can be thought of as a node in a graph. And then you draw a link between every pair of nodes, and you assign a weight to each link. And the weight is 1 minus the probability that 1 minus a fraction of time that the red message and the green message co-occur. Okay? So if this number is small, that means that red and green co-occur. By co-occurring, what I mean is first you take the message set and divide it into smaller bins, look at smaller intervals of time. And then so there are a lot of metaparameters that you have to deal with in these kind of problems. But let's say we can somehow deal with that. And then so you look at the co-occurrence probability and assign a weight. And then you remove all edges with large weights. A large weight simply means that these two messages never co-occur. Okay, so they're unlikely to be produced by the same event. And then you look for clicks in this graph. And this is not exactly the same algorithm that is used in this context, but it's very similar to other algorithms used in this context. And what we found is that the list of events found by this message, by this process, is the same as so if you apply this clustering algorithm versus our algorithm, the list of messages corresponding to each event looks exactly the same. But the clustering algorithm cannot tell you when an event started and when an event ended. Okay, so they need this information as well. And you can also do full Bayesian inference. Okay, so I can assume a generative model for this whole. So I broke it up into smaller parts called episodes. Instead, I could do a full-blown Bayesian inference. I could say that events are generated according to some probability distribution. Each event generates messages according to some distribution at certain times according to some distribution and so on. And then I can do a maximum likelihood estimation. And our algorithm actually matches it, except that this maximum likelihood estimation just is not scalable. Even for a very small set of messages, we just looked at 40,000 messages, for example, out of this 97 million data set. And we can see that the amount of time that it takes just grows humongously. It just simply doesn't work. Okay? But again, these are two different ways to validate what we did. And we also look to try to understand our answer visually. So this is, again, one small segment of the 97 million data set. So the x-axis is time, and the y-axis is basically the routers, and the y-axis is just the message ID. Okay? And after we run our algorithm for this part, you can sort of see that there are 1, 2, 3, 4, 5 events here. And 3 of the events are similar, and there are only 2 event types here, and there are 5 events in this picture. You can sort of visually see that what you're doing is correct. Because if you look at, so our algorithm says that this and this are essentially the same event types, and this event type and this event type are the same. You can't see this in the picture completely because I can't show you the probability distribution. But the list of messages that these events generate are the same. Okay? So that's it. So basically, our solution to this problem of detecting events from messages is to decompose the problem into 2 subproblems: change point detection followed by topic modeling. And you can prove that this algorithm has low computational complexity, is provably consistent, and has low sample complexity. And we were able to run this algorithm on a data set consisting of 97 million messages. And the way we validated this is to try to use other algorithms which either cannot run on the full data set, such as the full Bayesian inference, or clustering, which doesn't give you all the information that we need, but at least all the information that these various algorithms provide are consistent with our algorithm, and our algorithm is able to scale to a massive data set. Okay, that's it. Thank you. Yeah.
So the algorithm you had, it seems to be like a greedy type thing, right? You pick
Greedy.
in some way the first change point. You say, okay.
The hierarchical algorithm.
Right.
Yes.
Yeah.
Yes. The consistency result says that works. Yeah.
Okay, and then whatever measure this greedy algorithm's minima, it looks like it has this property that there's a diminishing return in selections.
Right. So at some point you would stop the algorithm because you cannot detect any more change points.
And in the end, it seems to be like some sort of a subset selection problem with a submodular like cost function, so to speak.
I'm not sure. It's more straightforward than that. All it is just the probability distribution changes, and you just need to figure out where it changes.
But you're doing this myopically.
Yes, I'm doing it myopically.
That has a diminishing.
I see. So you're saying that maybe there is a different way to interpret the algorithm.
And
Okay.
It works.
Yeah. Possibly. Yeah. Here we just looked at consistency and sample complexity, but maybe there are other ways to interpret it. Yeah, Neil.
So does your consistency result, it looked like the number of episodes K stays fixed, and you let M
Correct.
the number of
Correct.
events
Right.
go to infinity. But in principle, the more data you add, the more episodes you're going to see. So did you look into how, if you let
Well, I'm assuming that for the same, okay, this is, the consistency result is under our modeling assumption, right? So I'm going to assume that given n data points, the events happen at tau 1, n times of tau 1, or tau 1 over n and tau 2 over n, you're right. So you could have a different model, and then you could say what happens. Good question. I don't have a good answer to this. Good question. Yeah. So you're saying that what if the number of events scales with the number of with the amount of data that you have? We haven't thought about that. Yeah. Good. Yeah.
So can you divide the message into fixed size episodes? Then for each episode, just check whether the distribution has changed.
So which is roughly what this clustering algorithm does? You mean for the whole thing?
like we find one episode that distributes.
But then there is, so I guess one of the things is we have very few metaparameters to tune here. Okay, so the more and more metaparameters you have, then you have to also figure out how to tune those parameters. I mean, every machine learning algorithm will have some parameters, which shows something that doesn't have too many things to tune. But yeah, it's possible to do other things as well, but you may have to figure out how much that window should be, right? Yeah. Was there a question there? Yeah.
Yeah, so in your case you have sort of discrete events, right? What if you have a chain of events and given one sort of one error, if the messages, if the iterated messages come sort of increase sequentially, you don't have the same pattern, but it's sort of a
yeah, I mean, there could be other models, and I think that's the question was asked there. You could also have some dependence on the messages too. I mean, the first, as I said, we validated this in many, many different ways, and it worked for our data set. That's the only answer that I have. I think you can have more general models, and I think another interesting question, as I said, if the number of messages is roughly of the same, the number of types of messages is actually of the same order as the number of, there are many, many problems that we can make up, but for this particular data set, this worked. Yeah, I don't have anything more to say. Yeah, but good questions though.
Thank you very much.
Thank you.